It's entitled Autonomous Detection of Vehicular Wheel Alignment Parameters by Gerard Ragbir, and
Yes,
it's
good
pre-recorded.
from the transition planning. So the issue of execute.
Right, so
Good day, everyone. My name is Gerard Ragbir, and on behalf of my colleagues from the University of Trinidad and Tobago, Mr. Ameerali and Dr. Nadine Sangster, we wish to present our research on autonomous detection of vehicular wheel alignment parameters. So first, we're going to take a look at the problem, then the goals of the research, how they were achieved, and what we found. To start, we need to define some terms. Wheel alignment is the obvious first. This is a form of vehicular maintenance which many often overlook. It ensures that you always have optimal road contact and performance. Some vehicles only allow front wheel alignment and others require all four. There are many parameters, but the key ones that we're considering are camber, toe, and caster. We're going to take a look at these parameters now, starting with camber. Camber is viewed from the front of the vehicle, and if the top of the wheel leans inward towards the vehicle, it's considered a negative value. Conversely, away is positive. This changes the contact surface area with the road, and alterations to this can actually affect straight line motion as well as your cornering ability. Next, we take a look at toe. This is similar to camber, but taken from an overhead or an aerial view. When the front parts of the wheel tip towards each other, this is considered toe in, and conversely, away from each other, toe out. They ultimately affect the steering performance. And finally, here we take a look at caster. So, caster is worth noting that the angles do not actually indicate a degree of misalignment, but rather a function that affects maneuverability. When it leans away from the front, it's considered positive, and when it leads toward the front of the vehicle, it's considered negative. Now let's take a look at our objectives. So we began by trying to identify possible methods for detecting wheel alignment, then evaluating, designing, and developing a device for detecting these parameters, that is camber, caster, and toe. And then finally, we sought to benchmark this design against existing methods. Next, we're going to take a look at our methodology, starting with a functional analysis. So a functional analysis breaks down any process or procedure into functional blocks that are then evaluated separately and then combined at the end to produce a result. So we started by looking at how to collect some alignment data as well as any additional data. And this process is the obtaining process, so the data gathering process. Then whatever data we collected, we would then calculate the caster, camber, and toe. And then these values would then be compared to recommended values. And if any were out of alignment, or even if it's in alignment, this would then result in alerting the driver, which is more or less an alignment notification. Next, we take a look at our morph chart, which takes a look at all of the combinations and possibilities when making a final selection or multiple selections. So we started by taking a look at these parameters, the energy and data collection method. So there's a wired and a wireless option. The types of sensors, so an electric, magnetic sensors, acoustic sensors, optical, and in this case here, MEMS or micro electromechanical devices. Suspension types, these are just some of the more popular suspension types in use within most vehicles. Types of alignment, as we mentioned before, there's two-wheel and all-wheel, four-wheel alignment, as well as various types of strategies for mounting these final devices. Ultimately, the decision we selected involved a wired MEMS on a double wishbone on a front wheel type vehicle with a fixed mounting mechanism. Here we can take a look at the actual intended design for the IMU or MEMS version. So this is on a double wishbone, as you see here. That's the upper and lower arm. This is the wheel hub here. This is a side view. And you might notice that the ABS cable is here. And the intent was that both cables could technically be routed similarly and then observed and monitored via a computer control system, which most vehicles do possess nowadays. In this slide, we can take a look at the mounting strategy used, where one sensor was placed on the right wheel, one was placed on the left wheel, and one was placed and mounted onto the chassis of the system, which gives an indication of a fixed framework for calibration. Here we just briefly are going to look at some of the alternatives that we use. So the first being an acoustic sensor. The acoustic sensor would measure differences, changes in distance between multiple positions, and that would in turn give value for camber, caster, and toe. Similarly here for the optical version, it keeps an eye on the surface profile and then monitors changes in that. Now we're moving on to the results, starting with our camera results. So it's worth noting that this main section here is what we'll be viewing, and that this is actually from a much larger data set that was summarized. So the intended angle that we sought to get, 0, -1, +1, etc. And these were the actual values we got for both the left and the right side. And you will notice that it's actually within a degree or of certainty of each other, which we then verify here. So the values were pretty close, which is a very positive thing. Here we have our tool values. So it's worth noting that the table was actually split into data obtained from the IMU, as well as data collected from the actual calibration system, which was a Hunter Pro-Align industrial machine. It's what you would often find at a wheel alignment center. And for the most part, these are what the values were read out as by our algorithm, and this is what they actually were, based on the values and the parameters that we set in. And for the most part, there was a significant bit of overlap with some minor errors due to calibration. Finally, we take a look at the results for caster. Now, this is typically an adjustable parameter for sports and high-end vehicles. However, the vehicles that we had access to we were unable to get permission to modify the caster, and we attempted to simulate this data by creating a manually adjustable rig. However, that rig could not be used with the benchmarking aspect, so the data would not have been comparable. In conclusion, we evaluated methods for detecting alignment parameters using acoustic, optical, and MEMS methods. The design we eventually selected and implemented was the MEMS version, which was in the form of an IMU sensor. We calibrated and benchmarked the device against a known standard, that is against the Hunter Pro-Align machine. These are some of my references. Thank you very much. Are there any questions?
Thank you, Gerard. Another very interesting presentation, and up my street, so to speak. So I'm not seeing any questions in the chat right now. So while people formulate their questions and put them in there, let me kick off with a couple. Just to confirm this, so basically what you are presenting here is an onboard wheel alignment monitoring system for use in vehicles, right?
Yes, it is.
Great. And are any vehicles on the market right now which have such a system?
Not that I'm aware of. So keep in mind that this research would have actually been done a couple of years ago, and I haven't actually looked into like if there are implementations of it. But to my knowledge, I don't believe there is. There have been patents, however, in that space, in that time period where people have put forward algorithms to do it, but no one has actually looked at sensors or the actual implementation of.
Right. Arshad Mohammed is asking, is the vision to have this system replace the industrial systems? And I think that by that he's talking about the kind of systems you have in the wheel alignment center.
I don't think that that would happen anytime soon. There is refinement needed for these systems, but it is very possible to at least give an indication that your wheels have actually gone out of alignment, because one of the more popular things, one of the most popular things that tends to happen is people don't check their wheel alignment as often as they should.
Right. Yeah. Very good. So it's to alert the driver, and let him know he should go and make a check. So the Johnny Chu asks whether the implementation would be a live real-time detection that's embedded permanently on the vehicle.
So yeah, there are strategies that we had considered in the original work where we considered both a real-time system as well as one that only works upon startup. The real-time system would basically increase the relative cost. We did not actually look at cost as a factor since this was just a proof of concept, but obviously a real-time system would increase the amount of cost necessary.
Right, so that might partially answer my next question, which was about the selection of your sensor as an acoustic sensor. Because I wondered about the suitability of an acoustic sensor in that very noisy environment of underbody, on the vehicle.
Right. So in the initial proof of concept, so we did do a conceptual test to see how we could eliminate that noise. So in the actual algorithms, I believe it's actually on the paper. During startup, at least, the sensor would check for noise and then calibrate itself and then try to give a reading. But one of the issues with the actual acoustics and even the optical one, so the optical one was prone to basically issues with the actual aperture and the optical system. So the lens could become scratched over time, etc. And that would degrade the quality of the readings. And then in an acoustic system, the acoustic system would actually need to either be a moving system that then hides itself, because if you have debris and stuff while the vehicle is driving, you could actually damage the sensor. So it was one of the things that, it was one of the reasons why we did not go forward with that design.
All right, great. Thank you very much, Gerard. A nice system and a good presentation. Congratulations on that.
Thank you very much.